Welcome to our presentation on enemy character aging. I am Ahmed Al-Ghanem and my partner is Adham Khaled Hiyaz. The table of contents we're going to go through problem statement, summary of proposal, related work, proposed solution, progress report and results, and the next steps. The problem statement. We want to simply create a model that ages teen enemy characters into seniors and also does the aging by making senior enemy characters into teens. This is an example of the expected input and the expected output that we ideally want the model to have. The motivation is mainly that we want to learn about the generative adversarial networks or GANs, as they will not be covered extensively in the course. We want to get hands-on experience in the full ML cycle, including data collection, data cleaning, and so on and so forth. We want to be pioneers, and this will come in later in the presentation. And we simply wanted to have fun in a domain that we both enjoy. Now let's go to the summary of the proposal. GANs are networks that generate fake data. For example, this is data from this person does not exist. All of these people have been created by GANs. And GANs simply work by having two networks, a generative network and a discriminative network. A generative network generates fake images, and the discriminative network tries to identify the real from the fake, and the two networks kind of compete with each other. And yeah, that's it. The data sets that we looked at, these are the three. Feel free to look at the first two data sets, but the main issue was that they were unlabeled. We were not able to separate between teens and seniors. The third data set, we were able to separate between teens and seniors. The only problem that we had was that it had to be scraped. It was not ready to download, but we were able to do that. Let's go through the evaluation metrics. The most popular evaluation metric is human evaluation through visual cues. Obviously, this is very time expensive. It is not objective, and there are biases. However, it remains very popular because there is no consensus on another objective metric. There are variations of it, such as crowdsourcing through Amazon Mechanical Turk or other things. Average log likelihood is no longer a popular evaluation metric. It was introduced by Ian Goodfellow in 2014, in the same paper that introduced GANs, but it is no longer very popular yet, so we can go ahead. Inception score was introduced in 2016 by Salomons. It uses a pre-trained model, the Inception version 3. It measures image quality and image diversity, and it is a popular metric still in use today. Similarly, the Frechet Inception distance also uses the same pre-trained model, Inception version 3, and the FID was introduced by Husel in 2017, Husel and others. And it is also another popular metric that measures similarity between feature vectors of two groups of images, real and generated. Now Adam will walk you through the related works.
So the related works that we took inspiration from are three main papers that we're going to talk about. But first, we are the pioneers. We think of ourselves as the pioneers of this domain, as it was not really explored in other papers of character aging and de-aging of anime characters and not normal human beings. So what we use is image-to-image GANs. And we took inspirations from GANs that worked on human aging to domain transfer it to the anime. But of course, it needs to work on unpaired data sets because we don't have the image of the old anime character with its young version of itself. However, we have an unpaired data set of that. So the three papers that we took inspirations from are the phase aging and identity preserved conditional generative adversarial networks, which worked on unpaired data set and also works for human aging and de-aging, as I said before. And another one was the unpaired image-to-image translation. This one worked on unpaired data set, but it did not work for human aging or de-aging, but we also took inspiration from it. However, the main paper that we took inspiration from and based our model on is the Implementing Cycle GAN for Age Conversion by Matcha. And we based our model based on it since it worked for unpaired data set and also worked for human aging and de-aging, which is close to the problem that we are tackling. So as you can see here, the cycle GAN is different from the normal GAN since from the normal GAN since it has two generators. As we said, we have a domain A and domain B. Domain A here is the horses and domain B here is the zebras. What we need to do is to map domain A to domain B such that the horse becomes similar to takes the unique characteristics of domain B and apply it to it. It has two discriminators as first, when we domain transfer domain A to domain B, it goes to this discriminator and then calculates the GAN loss. And then when it goes back, it maps it back, this is the unique part of the cyclic GAN. When it maps it back from domain B to domain A back again, meaning that from zebras to horses, it passes to generator from domain X to Y, and having another loss function. And then the model needs to minimize both loss functions to end up with a model that takes domain A and transfer it to domain B, and taking the main characteristics of domain B while saving the essence of the domain A. As you can see here when we take that back to human beings and aging and de-aging, we see the original picture of the young young human, and we translate it to a more senior one while having the same characteristics of the original one. And back again and then it reconstructs it back to the young version of it, and vice versa. In the senior one, we want to transfer him back to the young one as the aging, and then it ages it back in the another generator. Our proposed solution is taking this architecture and applying it to our domain, which is the enemy. So we face some challenges that we would need to tackle in order to reach the solution. So first of all, we need to obtain a data set, and we had to scrape for it. And then this data set has a lot of variations, so we needed to have data cleaning in order for the model not to be confused. And then we'd also need some data augmentation in order for the data, in order to increase our data set. And we need to, of course, to do model modification, hyperparameter tuning to make it compatible with our domain. And then we also face some challenges, as enemy are actually different in their appearances, so the model was a little bit confused because of that. So now going to our progress and what we did in this milestone. First of all, we needed to scrape for the data, and we did a lot of scraping in order to obtain our data. And then we passed this data into a cropper in order to crop for the images of the faces of the characters. And then we had to apply our base model and then model the variations. So in the scraping, we had already a scraper, and as I said as mentioned in the proposal. However, we did a lot of modifications to it in order to improve its efficiency, and also we so that we scraped labeled images of teen and senior. Moving into the cropper, we used first we used a cropper in order to crop for enemy faces, but then this cropper did not work properly for a senior, so we had to find another cropper in order to work properly for the senior, and we used the one created by Curtin on GitHub. Our base model, as mentioned previously, it transfers domain A to domain B, and domain A here is the teen characters, and domain B is the senior. And then we ran it 3 times, one on 5 epochs and 18 epochs, both on 160 senior images and 1,200 teen images. But then we ran it one time with 15 epochs by 800 senior images to 1,200 teen images. So this gave us some results. As you can see, some pictures. That these are the translations from a young anime character to an aged one. As you can see, we can see here that some characteristics such as the white hair is learned by the model. However, of course, it needs more training and more hyperparameter tuning for better results. Now, Ahmed will take you through some of the variations we did.
Now, for the model variations, before I go through the variations, we need to specify what was in the base model and what we changed. So the input image size to the base model was 256 by 256, and there was resizing done internally to make sure that all images have that size. It used a very small batch size of 2, and the teen dataset, as Adam mentioned, was only 1,200 images. In the variations, we were able to increase that teen dataset to 10,000 images after we were able to do any more scraping. We also changed the input size to 64 by 64, and we also tried 128 by 128, and we also tried different batch sizes, 8, 16, and 32. Here are some of the poorer results that we had. At first, the image size 64 by 64, regardless of the batch size. We tried different values for the batch size, but it had a very slow learning rate, and it it kind of seemed to like memorize previous iterations, and it wasn't really good, yeah, as seen in the results. However, the image size 128 by 128 was very good in comparison, obviously, to the 64 by 64, and we kind of are still going to fine tune it even more and compare it to the 256 by 256, which Adham discussed, which even had a smaller data set. So we are kind of in between both, and obviously we're going to still look at more options. And now for the next steps, as I was just saying, we have to do some hyperparameter tuning in order to find the best results. We also need to do more data augmentation, specifically for the seniors, seeing as 700 images is a very small number, and we are probably going to overfit. So we're going to use translation, rotation, brightness control, and so on and so forth. We also need to do something that has to do with saving a loading model. We already tried to do this in this milestone. However, we had a few errors, and the loaded model refused to adapt its weights. So hopefully, I think I found a solution. However, we are not yet able to test it. So we are going to try to save and load model in order to like have longer epochs without Google Colab running out, or without extensive any consumption of local hardware. And thank you for your time.
Arigato.
Arigato.